usual assumption that we have this homogeneous, this uniform field where we can describe it as an acceleration of 9.8 meters per second squared throughout this building. I let go of something over here, it falls down to the ground. I'm going to describe it as accelerating, and if there's an x-coordinate attached to this particle, on the frame of the particle, then we're going to relate to each other's measurements according to this. X prime is equal to, let's say, the x of the falling frame, plus or minus, depends on how you define g, times t squared. Right? This is simply the acceleration formula. So if one says that it's standing still and the other one says it's accelerating, the relationship between the two obviously is given by one of the other's x plus or minus whatever half gt squared. Equation-wise, what's the transformation? We have one sees the other according to this. You can do a coordinate transformation in a regular xy plane, let's say something like this. You can do a coordinate transformation also in xt. If you have an xt, right here we're only considering two dimensions just for simplicity. So we have these two dimensions, time and one dimension of space, but we're talking about linear motion being accelerated, let's say straight down. And the relationship between the two can be something like this. In the same way that we have a coordinate transformation in this plane of space, we can have a coordinate transformation in this plane, so to speak, of space-time. And so we see this equation as a coordinate transformation. So in other words, going from the viewpoint of the planetary surface to the viewpoint of the free-fall particle, the free-fall particle claims it's inertial and we say it's accelerated, we see it as a coordinate transformation in space-time. It's a space-time coordinate transformation. Now, what is a uniform acceleration? We know mathematically it'll give us this, but let's look at it, since we know that we're talking about space-time, let's look at it in a little bit of a more sophisticated way. So, a straight line in space, y is equal to mx plus b, the xy axis. A straight line in space-time, as we spoke about, our inertial particle world lines have straight lines. X is equal to vt. V would be the speed, and it's the slope of the line in the tx, or the inverse of the speed. All right, so this slope over here is the inverse of the speed. And so vt, the speed, times t plus b, that's a linear relationship between the two. All right, so this is the equation of a straight line. Okay, now, a coordinate. We can see that what we're doing is equivalent to using curvilinear coordinates. Curvilinear coordinates simply means if you're going to change something like this, obviously this new x prime is not a straight line, it has the xy on it, right? It's going to be something like a y squared, okay? So here what we're doing also is kind of using curvilinear space-time coordinates, and that's the transformation that we're doing. So what we have is the sense that a gravitational field can be modeled by using curvilinear space-time coordinates. And that's the transformation that we're doing. Now, a coordinate transformation can't ever change physics. Coordinate transformation is just a different perspective. Like here we have a particle falling, we have ourselves, we describe it one way, the particle described, the frame of the particle describes itself in a different way. The description is not going to change the actuality of what's happening. It's a perspective. And one should always be able to change from one perspective to the other if one understands the physics. So in a uniform field, in a uniform gravitational field like in this room, at least according to the usual approximation, we can model what's happening with a coordinate transformation in space-time. And we know that if we use these kind of coordinates, we're going to see the inertial particles as accelerated. If we use the free fall particles coordinates, then it won't be accelerated. It'll see us as accelerated, which is fine because we feel these accelerated forces. So we're not inertial. We're not surprised to find that this inertial particle considers us to be accelerated information. This one will have some x prime 1 is equal to x plus 8 t squared, and this one has a different coordinate x prime 2, which is x plus b t squared, and so on. You'll have a whole bunch of different regions. Each one has its own acceleration, which of course does not change any of the physics. It's just changing the description. But we have a multiplicity, many, maybe an infinite many, regions in each of which there is some. We had this tx or xy, right? And you have a description that uses curvilinear coordinate axes instead of, let's say, these rectilinear and perpendicular coordinate axes. We're going to use some kind of curved lines as our coordinate axis. And you do transformation from one description to the other. Then, obviously, what seems like a straight line in one coordinate system, like this, if you start using some kind of weird transformations, you're going to get into stuff with different terms arising. It's not going to be immediately recognizable as a straight line, but by doing a coordinate transformation, you can't turn a straight line into a non-straight line, or vice versa. What you can do is take a straight line equation that's immediately obvious as a straight line equation and turn it into something that's still describing a straight line, but in a very non-obvious way. Okay, you can change the description, not the actuality. And therefore, each one has its own space-time coordinate transformation. Basically, in the same way that we were able to see an arbitrary gravitational field as a collection of accelerated plates or buildings, we can now see each of those accelerated plates or buildings as a coordinate transformation in space-time. A type of coordinate transformation which, of course, does not change any of the physics. It's just changing the description. But we have a multiplicity, many, maybe an infinite many, regions in each of which there is some coordinate transformation. Have the mathematical model which tells us we can model any arbitrary gravitational field by a collection of regions in each of which there is a coordinate transformation in spacetime. And we know that in each of those regions the coordinate transformation just changes the description, it doesn't change nature. Now we have a very interesting challenge. How do we find a mathematical model? We want to find some situation and its corresponding mathematics which has exactly this property, but we have to invent it. So you're going to have regions. This is our building over here. This is a building in some other country on the planet. This is a building on the other side of the planet. Everywhere, there's going to be some region where, in that region, it's going to be a uniform gravitational field. But you can always find some small region where, to the extent that you're able to measure, you have pretty much a uniform field. And so we'll model any gravitational field by a collection, a very large collection, maybe even an infinite collection of tiny or infinitesimal regions in each of which we can consider the field to be uniform. We can see that we have here a collection of regions, in each region of which what we're doing is equivalent to using curvilinear coordinates. So what we have is the sense that an arbitrary gravitational field can be modeled by a collection, finite, infinite, whatever, of finitely sized or infinitesimally sized regions, in each of which there is a curvilinear. So we have this very interesting idea that we could model an arbitrary gravitational field by a collection of regions, each of which has space-time coordinate transformation. So we're getting more and more sophisticated. So now, what does that give us? What is a collection of regions in each of which there is a curvilinear coordinate transformation, or equivalent to that? But basically, in the same way that we were able to see an arbitrary gravitational field as a collection of accelerated plates or buildings, we can now see each of those accelerated plates or buildings as a So what we have is the sense that an arbitrary gravitational field can be modeled by a collection, finite, infinite, whatever, of finitely sized or infinitesimally sized regions, in each of which there is a space-time coordinate transformation. So we're getting more and more sophisticated. So now, what does that give us? What is a collection of regions in each of which there is a curvilinear coordinate transformation, or equivalent to that?